Okay, so the one that you discussed, the indeterminate product,
Yeah,
was a little
yeah.
confusing to me. The F over 1 over G.
Okay, okay. Yeah,
I
those
just,
those
I
those
just,
are a little hairy. So let me just grab one. I don't remember which one of those I happened to do. But let me just grab 29
did,
does not look familiar to me. So let me
one
erase.
you did was,
I think I did 20. I don't know. I can do 28 or 29. I'll do 28. Because it has a log in it, and I wanna make a big deal out of that. So let's talk about indeterminate products, right? So in the video, if you watch the video on 4.5, there's a section on indeterminate products, there's a section on indeterminate differences, and there's a section on indeterminate powers. And it all begins with L'Hopital's rule at the beginning. So what is the thing? Let's just take I'm just going to write down 28. 28 says the limit is x goes to negative infinity. So 28, that pin's dead. It's the limit as x goes to negative infinity of x squared e to the x. Okay, sure I've got that copied correctly. Yes. Now, what is it about this problem that presents differently than, say, just a regular L'Hopital's rule problem? When we plug in negative infinity, we can graph both these functions. We know what x squared looks like. X squared looks like this. As we head to negative infinity on the x-axis, this grows without bound. X squared turns into infinity. The graph of e to the x, however, right, the graph of e to the x goes like this. This is a graph of e to the x. Again, as we approach negative infinity on the x-axis, we're heading to 0. Now, we so badly want to write down 0 for that answer. I mean, we just want to write down 0 because a number times 0 is 0. However, infinity is not a number. That's something that is just a fact. Numbers live on the number line. Infinity doesn't. So we don't know what this is. All right. So we call this, sticking with our indeterminate, we call this an indeterminate product. Okay, that's what we call this, indeterminate product. Now, that presents two options for its solution. Indeterminate products present two separate options. This is a function f, this is a function g. All right, so we have f times g, and that is not infinity divided by infinity. That is not 0 divided by 0. That is infinity times 0. L'Hopital's rule, remember, says, I'm here for you in two cases. And those are these two cases right here. So we're going to doctor this up. We're going to use algebra. Okay? What are we going to do? We're going to use a crazy rule that says 4 times 3 is the same as 4 divided by 1/3. There are 3 1/3 in every 4. So there are 3 1/3 in each of these 4s. So this 1/3 goes into 4 12 times. just like this side. Now, why did I put the 1/3 on the bottom? I didn't have to. I could have put the 1/4 on the bottom. Think of this as a quarter, right? Just think of it as a quarter. There are 4 quarters in every dollar. So if you have $3 and you're asking yourself how many quarters that turns out to be, there are 4 quarters in every dollar. That turns out to be 12. All of these are 12. Now, what is the justification for this? What is our motivation is a better word. Our motivation for this is a fraction. It looks like this. This is a fraction. It looks like this. This isn't a fraction. I don't want that. I want L'Hopital's rule, okay? Because when I multiply them, I don't know what I'm going to get. I don't know the answer. So what I said on the video when we were talking about indeterminate products is we're going to write this as F over 1/G, or G divided by 1/F, just like we did here. Am I going to put the G on the bottom? Am I going to put the F on the bottom? All right, but remember, we got to reciprocate when we put it down here. It's not 4 divided by 3 is the same as 4 times 3. You can't do that. So when we're given this problem, right, when we're given this problem to work on, we have to decide which one of these we're going to put down here. Now, I would love to tell you there are firm and rules about this, and there are firm rules. One of the rules says if you have a natural log, which we do not in number 28 if you have a natural log, it always stays on the top. I mean, make sure you write that down, because if you do not follow that rule, then this becomes more complicated, all right? And that's not what we're shooting for here. We're shooting for simplification. So what are we going to do to solve this problem? We're going to write limit as x goes to -infinity. We're going to write x squared times e to the x. And we're going to re-express this. Our motivation, if we're sitting for a quiz, we're sitting for a test, our motivation is we saw it's a product, and we learned in our notes and in videos and by reading the book and by listening to this lecture right here, we learned if it's an indeterminate product, this is my technique. This is what I do, right? This is what I do. Just like, when you're going to tie your shoe, you know what to do there. When we have an indeterminate product, this is what we do here. So I'm going to rewrite this as the limit as x approaches -infinity. And now I have to make a choice. I'm going to choose to put the e to the x on the top and the x squared on the bottom. And I'm going to tell you right now, that's the wrong choice, okay? That's not going to be nice. So if you want to stop writing and only watch, if you want to write in your notes, this is not going to be the way we're going to solve this problem. I'm going to do it the wrong way first to show you, oh, that's what Kevin meant when he said the wrong way is the wrong way. So what do we have right here? All right, what do we have? If we take a look at what we have here, let me change colors. If we take a look at what we have, as x goes to -infinity, we decided as x goes to -infinity, e to the x goes to 0, right? E to the x goes to 0. As x goes to -infinity, I get to square that. That's 1 divided by infinity is 0. So we magically, by rewriting it like this, made one of L'Hopital's versions appear. And that's what we're shooting for here. That's our goal. Now, logistically, what do we do at this point? We write equals, and we write an L dot R on top of that equal sign. Why? Because that tells the person reading our work, I'm about to use L'Hopital's rule. This is about to change. We're about to rewrite it, and we're about to take the derivative of the top and the derivative of the bottom. And before we do that, we have to tell the person who's reading our work, hey, by the way, I took the derivative. Otherwise, they're going to look at what we wrote down and think, what the hell? Why did you write that? So where do we go from here? We rewrite this. We got to do this part. We take the derivative of e to the x. That's e to the x. Now, 1 over x squared is really x to the negative 2, isn't it? Isn't that, I mean, that's a lot nicer. So if I want to take the derivative of this, I could instead just take the derivative of this. Now, what does that work out? That turns into negative 2. Down comes a negative 2. And then I take away 1, x to the negative 3. So this is negative 2 over x cubed. So I'm going to put that right here. Now, I'm going to draw a line. Try to make this a little easier for you to see. Take a look at what we have there. This is this. This is what it is. Negative 2, right? Oh, I'm sorry, that's supposed to be negative. No, that's correct. That's correct. This is negative 2 x cubed e to the x. Look at our original problem. Our original problem is 1x squared e to the x. Our new problem is not better, it's worse than the old problem. If that happens to you when you're doing an indeterminate product, don't buy a lottery ticket that day. Just don't buy one. It's not a good day for you. You guessed wrong. And you guessed wrong. Typically, we want to leave polynomials in the numerator if we can. Okay, if we can. So this is what it looks like, right? Up through right here. This is what it looks like when it's going off the rails. When you're like, oh, I don't feel good about what I'm doing here. Am I doing it right? Yes, you didn't do anything. No one made a mistake. I didn't make a mistake. There's nothing wrong on this board. Everything's right. It's just not getting better. It's getting worse. I went from x squared to x cubed. I went from a coefficient of 1 to a coefficient of negative 2. That's bad. So what does that tell me? That tells me I'm going to start again. I'm going to start again, and I'm going to do it the other way. Now, again, if you're taking a test, you may want to think to yourself, oh, I remember Kevin telling me I should leave my polynomials in the numerator, because that's what he said. So we should leave our polynomials in the numerator. Now, again, we have to write this as a reciprocal, okay? No one's typing anything, so I'm assuming you guys are either all asleep or all following along. By the way, that's not your cue to start typing madly. So, where do we go from here? Well, if we take a look at this, negative infinity squared is infinity. Right? E to the x at negative infinity is tiny. It is a tiny number. It is barely above the x-axis. That's 1 divided by tiny. That's also infinity. Hopital's rule. So we write equals, we put an L dot R over the top. We rewrite our limit. Oh, I am so sorry. It's supposed to be negative infinity. We take the derivative. Over here, I'm going to do some scratch work over here. 1 over e to the x is e to the minus x, isn't it? So when I want to take the derivative of this person, That's the derivative of this person. The derivative of e to the minus x is minus e to the minus x, right? We write e to the minus x because that's our rule for the derivative of an exponential. And then we take the derivative of what's on top. The derivative of what's on top by the chain rule is going to be -1. So we know what that equals. That's -1 over e to the x. Okay? So what do we get here? We get -1 over e to the x. And now we ask ourselves, what do I get when I plug in -infinity? Well, when we plug -infinity here and multiply by 2, we get -infinity. By the same argument we used up here to say it was positive infinity, this is going to turn into -infinity. Okay, don't panic. It was L'Hopital's rule a second ago. It's L'Hopital's rule again. That's all this means. We're once again right here. So we're just going to write equals LR, and we're going to copy this part. You can use L'Hopital's rule as many times as it applies, okay? As many times as it applies. All right. So where do we go from here? Well, we take the derivative of the top. That's going to be 2. Okay, we're done with L'Hopital's rule now because my top is 2. That is not 0, and that is not infinity. So this is the end of L'Hopital's rule. We take the derivative of the bottom, all right? So what are we going to take the derivative of? Well, this time we're taking the derivative of this, which turns into this. So I have 1 over e to the x, all right? Now, what does that equal? Well, when I put infinity down here, I get 1 over infinity, right? Positive, I get 1 over a positive tiny number. So this is 2 divided by 1 divided by a positive tiny number. It's really important that we notice that that's positive tiny, because when an infinitely small number is divided into 1, that is a huge number, right? 1/1000 divided into 1 is 1,000. So what does this look like? This, the bottom, right? Just the bottom. And this is all mental math. We do this in our head. There's no picture here. There's nothing. We just have to think our way through this. When we put -infinity in here, we get a number barely bigger than 0, but it's positive and it's tiny. When that goes into 1, we get a huge number on the bottom, and we get 2 on the top. Well, 2 divided by a positive huge number is going to be 0. So our answer turns out to be 0. Okay. So we can't multiply here. It's a coincidence that our answer here, and if we would have done this, we would have gotten 0. This was not a waste of our time. We can't do that. There are problems, and I'll put one on the quiz or on the test probably, where you're going to look at this and you're going to think, well, 0 times this is 0, and you're going to write 0 here. And if you do the work, you're going to get 8. Okay, this is indeterminate. We are not, the rule that many of you want to use, you want to use a rule that says this. And that rule is valid when A is a real number. All right? Infinity is not a real number, so we cannot use that rule. You can't use that rule. You must do this. I mean, if it's a multiple choice question, you're going to get lucky, and you're going to bubble in D or whatever the answer for 0 is because you got 0 up here. But on the test, I'm going to make it turn out to be something other than 0 because I want to see if you can do the work. I want to see if you can do the work. All right. So that's number 28, and that's an indeterminate product. All right. Does anyone else have any other questions you want me to work on? They don't have to be from 4.5. They can be from 4.4 or 4.3 or 4.2. Because if you don't, I'll move on and start talking about 4.6. But if you want other questions taken care of, I mean, we still have, like an hour to go here. We don't have to stay here. Look, you can leave when you want to leave. I'm not, I can see your names up there, but I'm not going to suddenly go, oh, Alyssa left. Oh my gosh. So it's okay. And besides, if Alyssa left, I wouldn't know which Alyssa it is. All right. So I left this up here. I'm going to erase this now. I'm going to erase this now. Okay. Well, nobody else has written anything. So what I'm going to do now is talk about 4.6. Now, I've got a video on 4.6. In that video, I worked out several examples. However, I'm going to work out several more examples tonight. They're going to look just like the examples in the video. The beauty of the video is you can watch that over and over and over and over and over and over. Every single, you can watch that as many times as you want. You get confused, you back up. What is there about optimization problems that make them so magical? They're word problems. And for some of us, we just immediately default to fail when we get a word problem. That doesn't have to be your approach. First of all, optimization problems are, if we follow the steps that I'm going to give you tonight, optimization problems are pretty approachable. Okay? We can get ourselves in trouble. Don't get me wrong here. We can get ourselves in trouble. And the reason we get ourselves in trouble with optimization problems, more often than not, to be perfectly honest with you, is you start doing what you're doing. I mean, I see this on your tests, not yours, I haven't graded yours yet, but you start working on what you're working on, and then you think to yourself, oh, there's no way this is right. And you just quit. And you're actually on the right track. But things start to get a little, complicated, and you start to doubt yourself. So, yeah, the next exam covers which sections? That's a great question. I think it stops. Whenever it is, it's on your syllabus. It's going to be the same day. I believe it covers all the way through the end of chapter 4, and it might even cover 5.1. But I'll have that for you on Wednesday. I'll look that up for you on Wednesday. So I'm going to work out some examples for optimization problems. Now, before I can do that, I'm going to have to walk next door and grab another calc book, because I know all the examples that I've done on the video are out of this book. And so I want to grab some more examples, and I can't make optimization problems up off the top of my head. So you're going to give me a second. It's going to be like 30 seconds, but I'll be right back. All right, I'm back. it sounded like geometry there for a second. That's because my wife's teaching geometry out there to her classes. Let me, I just grabbed another book here. Let me find some optimization problems. Hey, look at that, optimization problems. Okay, so I'm going to do examples. I will write the problem in some shape, manner, or form on the whiteboard here so that you can write the problem down as well. Again, I've worked out many of the homework problems on the video that I did for you on this section. And there are obviously a myriad. Yeah, Adam, the next exam is a Zoom group test. You guys just have to start your own Zoom group off to the side, and I'll never know, right? I'll never know. So let's take I'm just gonna throw this book over here where I can see it. And in case you're wondering, earlier in the video, if I looked like, you know, I hadn't seen the sun for a long time, it's not that I'm not going outside. It's, I have two construction lights set up over here, lighting the whiteboard. So I've got 1,000 watts going in here, and it's very bright, but hopefully everybody can see. No one's complained yet about not being able to see. So I'm assuming this is so much better than what I was doing in the past. So this is school for us now for the rest of the year. So here's a problem that we're going to work on. Okay, I'm going to do step by step by step. I'm going to do a lower step problem, then I'm going to go up a level, then I'm going to go up a level, then I'm going to go up a level. My intention is to do 4 examples for you, each one getting a little more involved. Let's use that word, okay? Let's use that word. So here's where I'm going to start. I'm going to start with a problem that says this, okay? It says, so this is our example. We want to find 2 positive numbers whose product is 192. And whose sum is a minimum. Right? This is what a typical optimization problem looks like. Is that actually on the screen or is it off the screen? Is that out of view? You can see it? Okay, because on my screen is this big, so it's very difficult for me to see whether you can see. That worked. Okay. So hey, oh, it's going to be 1 week, 2 weeks from tonight. You'll be meet my puppy. So this is the typical optimization problem. This is what they typically look like. So what does it say? I mean, they're usually this short. They tell us some piece of information, right? I call this the Easter egg. Right? That's the thing that we forget to look for sometimes. And if we forget to look for it, we can't solve the problem. So in math, we call those pieces of information an Easter egg. What do we want to do? We want the sum of these 2 numbers to be a minimum. So we want to let X be my first number and Y to be my second number. And I want the sum, right? We want to find the minimum of S. Now, we are rocket scientists when it comes to minimization. We have done so many sign tests. If you've done the homework in 4.3 and 4.2, you are sign tested out. You can sign test with everybody on this planet. We know what we're going to do. If in a calculus book it says find the minimum of something, we know we are going to find S prime and set it equal to 0, or find where S prime fails to exist. This is how we find the minimum of, or maximum of anything. When you're in Calc 3, you're still going to be minimizing and maximizing. And forget Calc 2, you're going to do it there too. When you're in Calc 3, multivariable calculus, you're still going to be doing mins and maxes, and it's still going to be this. Take the derivative. When does it equal 0? When does it fail to exist? It's never going to change. This is how it works. That's the one redeeming quality of calculus, is once you learn something, we just use it over and over and over again. I mean, it's the only thing we do. It's like, okay, I learned how to do that one way. I'm going to keep doing it like that. If somebody else wants to be exciting and discover another way, hell, go do it. But we're not going to. We got one method. We're going to do that. So I want to take the derivative of this. Okay. Now, make sure you write this in your notes. I make a big deal out of it in the video. I say it over and over and over in the video. Before we can take the derivative of this, we must have one and only one variable. All right? So we must eliminate a variable. We can't take the derivative when there's more than one variable. We don't know how. We're in single variable calculus. I am pretty confident that, that we don't get to multivariable calc until, back here in chapter 13. Yeah, that's multivariable calc. But we're not there yet. We're not back here in the back of the book. We're still in the single variable part of the book. So we have to have one variable. Right now we have two. This is where the Easter egg comes in. The Easter egg is always here in these problems to eliminate a variable. That's what it's for. What do we know about X and what do we know about Y? Over here on the side, we know X times Y is 192. That's what we know. It says their product is 192. Well, if X times Y is 192, we know Y is 192 divided by X. Now, if you're wondering, why did I solve for Y? Why didn't you write, Kevin, X equals 192 divided by? You can do it either way. Nobody cares. It doesn't matter. It's not important. It's completely irrelevant. I just picked this one. Now, what are we going to do? We're going to come over here and we're going to put this in our equation. Every optimization problem you're going to ever successfully complete works just exactly like this. We're going to rewrite this. It's going to look just like that. Okay. How many variables do I have? One. Now I take the derivative. We must eliminate a variable. So what part kind of can't you see? How far is it the top that's disappearing? Nobody's typing anything.
I see everything.
You see everything? Okay.
I do so far.
Yeah, it's good to go.
Okay. All right. Well, that's good enough then. I don't know. Maybe Kylie's just trying to just dog me. I mean, that's
Perfect. Probably in the way.
Where did Kylie even go? Is she still even here? Maybe she's still here.
I'm able to see the board,
Okay.
all of it.
Okay.
Yeah.
Make sure. I don't want to leave anybody hanging. I mean, that's not polite, right? All right. So we're going to take the derivative of this. Okay. Because remember, that's how we minimize or maximize everything. When somebody tells you we've got a big problem, you tell them, well, we're going to make the problem smaller. I'm going to minimize that problem. Let me take its derivative. They won't get the joke, but you'll laugh your ass off. You're hiding off. I'm sorry. I'm in a room with, I'm literally doing this on top of a pool table where I do a lot of cussing because the balls very seldom go where they're supposed to. So I apologize. So what is the derivative here? The derivative of x is 1. The derivative of 192 times x to the negative 1 is going to be 192, right? That's my constant. The derivative of x to the negative 1 is negative 1 x to the negative 2, right? Because I take away 1. So what do we get here? We get 1 minus 192 x to the negative 2. That's our derivative. Now, what are we going to do with that? We already know what we're going to do with that. We know that as soon as we saw that word, we knew we were going to set it equal to 0. All right? We knew we were going to set it equal to 0. So this is where, if you've looked at the videos, we say things like this. S prime equals 0. S prime fails to exist. All right? And we start here. We start here. We say 1 minus 192 x to the negative 2 equals 0. That gets us 1 equals 192 x to the negative 2. I moved it to the other side. Put the x squared over here, right? Multiply both sides by x squared. And we get x squared equals 192. So does anybody know the square root of 192? I don't know the square root of 192. What's the square root of 192? I think it's just the square root of 192, right? Isn't that what it is? Because that's not a perfect square, right? 144 is 12, 13 is 169, 14 is ends in a 6. 15 is
8 root 3.
Yeah, so that's what we got, right? 8 root 3. Thank you. So
Thank
x,
you.
8 root 3. All right, that's what it is. Now, what about fails to exist? We got to check that. We got to check that. When does 1 minus 192 x to the negative 2, when does that fail to exist? Well, another way to write that is 1 minus 192 over x squared. That's going to fail to exist when x equals 0. Now, for most optimization problems, this piece right here, this piece is almost always NA. Unfortunately, I said almost always instead of always. So we have to check it. Why doesn't it apply here? Because it's telling me my first number is 0, right? That's what it's saying. My first number is 0. X is 0. That's my first number. And when I go try to find my second number, I got 192 divided by 0. Well, that's undefined. Plus, the instructions say find 2 positive numbers. X is not positive, so this gets thrown away. So this is my first number. Right? This is my first number. My second number, right? My second number then is going to be 192 divided by 8 root 3. Those are my 2 numbers. Whatever they give us, well, we know what we get when we multiply them together. I mean, we can all see what we get when we multiply them together. If you take 8 root 3 times 192 divided by 8 root 3, you're going to get 192. And that's the smallest 2 numbers that sum, that they have the smallest sum. You can pick all, you could say, well, you know, Kevin, I'm going to use 192 times 1, right? That equals 192. What's the sum? 193. Well, what you and I have proven over here is the sum of these two numbers is smaller than 193. In fact, it's the smallest sum of all sums possible that satisfy our condition. This is what optimization problems do. We use this in the real world more than anything else I'm going to teach you at all. I'm not saying calculus isn't used in the real world. It's just Calc 1's not very often used in the real world. But this, we use this every single day in every single manufacturing plant in the world, right? I want to make a box. I want to use the least amount of cardboard. I want to make a car. I want to use the least amount of metal, right? I want to administer a drug. I want to use the least amount to solve the problem. All of those are minimization problems. When you own a business, you want to maximize revenue. You want to maximize profit. Those are maximization problems. So we use this, you know, if you're a NASCAR engineer, you're trying to maximize speed. There are NASCAR engineers, I think I've told you that in class. I mean, that's a literal degree you can get in engineering, but not on the West Coast. We don't have any schools that offer it here. North Carolina, they have a world famous NASCAR engineering program there. And you can go get your degree and learn how to make cars go fast. So this is what an optimization problem looks like. I'm going to do another one. I'm going to do another one. It's going to be a step up from this one. A step up. All right, so let me pick another one here. So that's a very typical optimization problem where they give you some condition about two numbers. Let's pick another one here. A rancher has 200 feet of fence. Okay, so this is another. I did one similar to this on the video, but this is going to be different. So we have 200 feet of fence. Okay. And we want to enclose two adjacent rectangular corrals. All right. We couldn't do this on the last optimization problem, but we can on this one. Sketches are significant. If you don't have a picture, usually you don't get an answer, okay? The only ones we can skip the picture on are the ones like the one we just worked on a second ago, where we had, hang on a sec, got to plug the, I got to plug in the Surface Pro here before you guys all disappear. There we go. So with the numbers, we couldn't draw a sketch. Here we have a sketch. We're going to draw the sketch. And what's the sketch say? It says, I want to build a pen that's made up of two adjacent rectangles. And in the book, they have a drawing. So this is why I know this is the way to draw it. In the book I'm working from, they tell me those are both X and this is Y. Okay, so that's how I know this dimension is the same for both of them, because they told me in the book they're going to be two adjacent rectangles and they're going to be the same size. Okay, and what do we want to do? We want a maximum area. There's no reason to take 200 feet of fence and build the smallest corral possible. That doesn't make any sense. We want to build the biggest corral possible. Okay. Now this is our Easter egg right here. Got to remember to use that. We got to remember to use that. We want to maximize the area of this. Now, in essence, this is just one big rectangle. I mean, it's just one big rectangle. This side is 2x, that side is y. If we're going to maximize the area, area is what they want me to maximize, I need a formula for area. Area is length times width. But what do I have for my length? I have 2x. And what do I have for my width? I have 1y. Okay. And just like the last problem, I mean, it happens every time without fail. Two variables. Two variables. We got two variables. And I can't take the derivative until I eliminate a variable. Now I have to use the Easter egg. I got to use the piece that's given to me. What do I know about this whole setup over here? I know this is also x. I know this is also x. I know this is y, and I know this is y. Right? Those dimensions are given. It's a rectangle. It has to look like that. So we know the perimeter of our field, or our corral. The perimeter is x, 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 y, y, y. The perimeter is 4x plus 3y. But we also know how much fence we have. We have 200 feet. And here is our magic second equation given to us by the Easter egg that allows us, hey, okay, I did my pink pastel for the Easter egg. Hey, that's cute. That allows us to eliminate a variable. All right. Now, again, I'm just going to solve for x. Okay. So I'm going to get rid of the y. So what does that get me? It gets me 3y equals 200 minus 4x. Y equals 1/3 times 200 minus 4x. Okay? This happens every single time. Every time this is going to work out like this. Every time it's going to work out just like this. We're going to get two variables. We're going to make one go away. It never fails. Every problem is the same. If instead of reading the words and thinking, oh, this doesn't sound like the problem I did last time. The problem I did last time was about two numbers that added to 192. This is about some dude building a field. I mean, building a corral. No, it's the same problem structure. Okay. So where do we go from here? Well, we come over here, right? We come over here and we eliminate our y. We rewrite this as a equals 2x times, and our y is 1/3 times 200 minus 4x. Now, we can put the 2/3 out front. We can multiply the x inside. And we get this. One variable. Voila. Right? I mean, if you got money for doing this kind of magic, I'd be rich. So what can I do now? I've eliminated my variable. And as I told you in the video, once you eliminate the variable, that's when you take the derivative. So what do we get? Well, we get 2/3, right? That's a constant. That stays out there. The derivative of 200x is 200. And the derivative of 4x squared down comes to 2. So we get minus 8x. Okay. 200 minus 8x. Now, where do we go from here? Same place we go with every max and min problem. A prime equals 0. A prime fails to exist. All right? Every max and min problem, over and over and over. Again, if you've done the homework in 4.3, you wrote this quite a few times. Sorry, I keep stopping to take a drink because it's warm in here. So where do we go from here? We take this and we set it equal to 0. So we get 2/3 times 200 minus 8x equals 0, right? We can multiply both sides by 3/2, that goes away. So we're left with 200 minus 8x equals 0, or 200 equals 8x, right?
It's equal to 25.
And so what do we get here? We get 200 divided by 8 equals x, and we can simplify that. If we divide 2 into both those, we get 100 divided by 4, or we get x equals 25. Okay, so x is 25. That means this dimension right here is going to be 25. Now we have to find y. Well, we can find y. We have a formula right here for y. So if we want to, if we want to know y, and the problem specifically says what dimensions should be used. So we want to find y. So y is going to be equal to 1/3 times 200 minus 4 times 25, which is going to be 200 minus 100 times 1/3, which is going to get us, wrong, 100/3. So y is going to be 100/3. Now we could check, right? We could check this. Oh, I skipped this part. Why did I skip this part? Well, I skipped it because this is a polynomial. Polys never fail to exist, right? So that goes away. Now, does this really work? Does this really, it should, hopefully we didn't do anything wrong and we didn't. So what is this supposed to add up to? It's supposed to add up to 200 feet of fence. Well, we had a 25 and 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 we had 100/3 and we had 100/3 and we had 100/3, right? This is a sloppy check. Well, this is 100. This is 100. 200. Okay. All right. So this is what an optimization problem looks like when you throw in a sketch. All right. Same steps. Same steps. Same exact steps. We're not changing anything. The story changes. The picture changes, but the steps never change. They're exactly the same. So I'm going to do 2 more examples. 2 more. I have nothing else to do tonight. By the way, I'm now teaching BHS during the daytime. So never seen so many high school kids so excited to go to school. I think they're a little bored. Hey, here's a real interesting story. The people behind me had a party last night. That was good. In their backyard, they probably had like 35 people up there. It was like, oh, okay. Good for you. All right, so where do we go from here? Let's look at another problem that would be similar to a question like this. I want to make sure that I'm just checking over here. Okay. So here's another problem just from this book. It says, and this is another typical problem. Find the dimensions of the largest rectangle that can be inscribed in a semicircle. of radius r. Now, historically, I mean, I've taught 20 years. I've taught AP for 20 years. This is the kind of question that my students typically would ask. Can we meet the night before the AP test and sacrifice a goat and pray that this question is not going to be on the AP test? And I really don't get it, because the question's not that bad. I mean, it's really not. We'll do it right now, and I'll show you it's not that bad. I don't know what there is about this problem that you want to fear. So we need a circle, a semicircle, right? So we have a semicircle. I'm not very good at circles when they're flat. I'm really good at circles when they're on a board. So we have a semicircle. So this is our semicircle right here. So we're going to get rid of this part. Okay, so we have a semicircle. If you're amazed at the semicircle on the video, it's because I cheated and traced the Tupperware dish. I can't lie to you about that. So we have this semicircle, and they want us to inscribe a rectangle. All right. So we're going to have a rectangle that's going to go like this. And they want us to maximize the area. All right. Gonna have, you know I'm going to have to move this. It's driving me nuts. Be with you in about an hour, right? This drawing guy, be right back. No problem. All right, so we have this. Now, what do we know about this? All we know is the radius is r. Grab another color here. We know this dimension right there, r. Okay, that's all we know.
Oh, good. Drag racing. That's great. Social distancing.
I think that's all based on interpretation. You know, maybe these are really close people and they spend more time, you know, to them, maybe this was far apart. I don't know. They're new neighbors. There's a big block wall. I don't look over there very much. So what do we know? Here's what we know. This is where everybody seems to think their train comes off the tracks when I do this. I'm going to put a dot right there, and I'm going to tell you that that point is XY, because Lord knows we have never called a point in the plane XY in our entire lives. I mean, this is awe-inspiring. I mean, you know, I can probably just go around the country just doing this and having people go, oh, and just calling out my name. No, I mean, we always call that point XY. Now, what does that tell us? That tells me this dimension right here is X, isn't it? And this dimension right here is Y. Now, if you take a look at that red rectangle, that looks a whole lot like a field built by a farmer with 200 feet of fence that's split into two rectangles. I mean, I'm so sorry, but it looks a heck of a lot like that to me. I mean, it looks so much like that. It looks like this over here is probably X. So it looks to me, I mean, if I had to, you know, just first glance, if someone were to ask me, you know, here's $10, tell me how long that side is, I'm going to tell them that side's 2X. And they want the largest rectangle. We know what that means. That means they want us to maximize area. And we know the area of that rectangle. Now, this is completely a coincidence, by the way, that this looks just like the previous problem we did. I did not plan this out this way. I'm either really excited or really frustrated, one of the two. Now, it is different, right? Because last time we knew how far it went around that rectangle. We knew that was Y, and that was Y, and that was Y, and that was X, and that was X, and that was X, and that was X, and they added up to 200. And we knew that, right? We don't know that now. We don't know how far it is around the rectangle. We do know we have a problem, though. There's one variable, two variables. That's one variable too many, right? That is not social distancing right there. That is definitely not. So we need to eliminate one of those variables. Now, how are we looking at this picture? I mean, okay. If only there was something on that picture that would allow me to write an equation with an x and a y. I mean, if there was only like, you know, a rhombus or a pentagon or a hexagon or a triangle like this one. Which says that x squared plus y squared equals r squared. Pythagorean theorem, right? I mean, that's the Easter egg right there. It wasn't given to us up here. There was no Easter egg in the writing. The Easter egg was in the picture. So when we drew the sketch, we're like, hey, that's a right triangle. I know what to do with those. I'm very good at right triangles. Right triangle is my sweet spot. Yeah, everybody can hit a right triangle. I mean, a Houston Astro can hit a right triangle. So, ooh, threw that in there. So what does this give me? This gives me y squared equals r squared minus x squared, right? So what does y equal? It equals this. But that's not rocket science. I do not understand why my calculus students hate this problem. This problem's in your book, by the way. I think it's number 17. It's in every calculus book. And more often than not, I'm not going to lie to you, it's on the AP test as well. Well, what are we going to do? We're going to come over here and we're going to do the same thing we've done on every other optimization problem. We're going to make the variable go away. Okay. The one thing about optimization problems you can always depend on is, again, you can go back and watch the video over and over and over again. Do your problems as you watch the video. Just let me guide you through your problem. There's going to be a video example, because there's 4 examples on the video as well. Or maybe there's only 3, I can't remember. There's an example that's going to look like your homework problem. Just play the video over and over. It will make sense. Watching things once, come on, we don't watch Modern Family once. If we're not going to watch, Cam once, then I deserve at least the same respect. And I was able to say that with a straight face, only because you guys aren't in the room, by the way. So what are we going to do here? We know what we're going to do, right? We're going to take the derivative. Now, I don't like the way that's written, so I, like you, I'm going to write it like this. And I'm going to do the product rule, just like you are. Right? So we take the derivative of the first person, that's 2. We write down r squared minus x squared to 1/2, right? F prime g plus. We write down the first person. We take the derivative of this. Now we can all do that. We've done that so many times. Down comes the half. The new power. Take away 1. Minus 1/2. Now be careful. Here's where you could, not you won't because you're too good, but you could. If you're going too fast, you can make a crazy mistake right here. You have to take the derivative of what's inside. R is a constant. It's not a variable. This circle's not growing. This semicircle's not changing size. R is a constant. It's a constant. So it's going to stay just this size. So when we take the derivative of this, we get 0. When we take the derivative of this, we get negative 2x. This is a constant. Now what happens? Oh, you know what's going to happen. This cancels this, right? Those cancel each other out. And we're going to have to factor. We're going to do that crazy factoring thing that we've done 5, 6, 8, 12 times already in our lives, where we have to take out the negative power. And we know how to do that. We write minus 1/2 right there. And we write minus 1/2 right there. We know if we write those down, we're going to get the problem correct. We know that, okay? If we don't write that down, there's a chance, not for most of you probably, but for me, there's a chance I'm going to screw this up. I mean, come on, I'm a 2-time algebra loser here. So where are we going to go from here? We're going to look at this. We're going to go, well, there's a 2 and there's a 2. So I'm going to factor out a 2. I take out the smallest power of r squared minus x squared. The smallest power is -1/2. So that comes out here. Now what's left? We took the 2 out. This is going to be 1/2 minus 1/2. That's 1. All right, so that's to the first power. So we don't have any power on that. We can drop the parentheses. The power is 1. What do we get over here? We get an x. We get an x. We have a negative. What's this going to be? -1/2 plus 1/2. That's to the 0 power. That's gone. Now I do that exact same factoring on the video. Different problem, same exact factoring. So if that went by a little fast for you, don't panic. You can go watch it on the video. Now, this is what we get when we factor. Now we can all simplify that. This is to the first power. That goes on the top. So I have a 2 on the top. I have an r squared minus 2x squared on the top. And on the bottom, I have r squared minus x squared to the 1/2. Okay, that's my derivative. Same steps as the farmer's field problem. A little hairier. I told you they were going to get hairier, so we went through a little hairier. All right, a little hairier. Now, what do? We do the same thing we've done. A prime equals 0. A prime fails to exist. All right, we're not going to change it up now. This is what we do for optimization. This is what we do for mins and maxes. So when does a fraction equal 0? Right? That's what we got to ask ourselves, because this is a prime, right? This is a prime right here. When does a fraction equal 0? When the numerator is 0. Well, 2 is not 0. So that means r squared minus 2x squared has to be 0. Now you and I can solve that. R squared equals 2x squared. R squared over 2 equals x squared. Square root of both sides. R divided by the square root of 2, that's x. Okay, that's x. But when does this fail to exist, right? When does it fail to exist? Because it has a denominator. It fails to exist if we get a 0 on the bottom. That means r squared minus x squared, because who do we take the square root of to get 0? We take the square root of 0. So r squared minus x squared would be 0, which would mean r squared equals x squared, which means r equals x. Now, those are our 2 options. One of them is bogus beyond all bogusness. This one makes no sense. Look at your picture. What happens if x is the same as r? Right, look at your picture. If x is the same as r, then this side of the rectangle would go all the way to there. You would have no height. That would not be the largest rectangle. That would be, because this circle has radius r, right? So we all know if that's a radius, that's a radii. So we all know that's the point r comma 0. And now we would have no height. So this once again gets thrown away. And now they asked us to find the dimensions of the rectangle. Unfortunately, they still got the pen flip. Unfortunately, we found the dimensions of the circle. We didn't find the dimensions of the rectangle, right? We found one dimension, I guess. We found x, right? But we need y. Where are we going to go to get y? Right here, right here. You know what y is, okay? Now, smart is what you are, not what you aspire to be. You are smart. So when I want to find y, right, I could put x squared in here. I could put x squared up here. I could use this equation just as easily as this equation to get y. I think it would be a little easier if we use this one. This one says y squared equals r squared minus x squared. We have x squared written right here. Now, let's think this through. So many of my calc students get to this step, and then they're like, this is minus a half of r squared. So that's a half of r squared. Which is r squared over 2. So what does that mean? That means our y, we got to take square root of both sides, turns out to be the same as our x. Our y turns out to be the same as our x. It's not a coincidence, by the way, that when I drew this picture, right? When I drew this picture, this turned out to look like a 45, 45, 90 triangle because it turns out to be a 45, 45, 90 triangle. The x and the y are the same dimension. Okay. All right. So what else can they ask us to do? While I was thinking about the fact that I told you I was going to do 4 examples, I was thinking about that while I was doing this example. I can't really think of what another example. I'm going to take a quick gander at your book. I guess there's I'm perusing your homework assignment for just a second. I think that those examples would get you through all the example I was going to do for my 4th example. They don't have any problems assigned that bad. I mean, they really don't. They didn't assign any of those problems. So I'm just going to hold off right here and not confuse you any more than, you know, perhaps you've already been confused. Hang on just a sec. I'm getting well. I got to do a little work here. See if I can. Hey, I'm back. I'm still here. I haven't left. So, and look, it's 7:32. We're actually getting out of school early tonight. All right. So that's 4.6. I'm not really sure what the next section is. I don't know if it's, hold on a second. All right, it's 4.7. So here's what I can tell you about 4.7. Wednesday night, have a calculator handy. All right, it's gonna help a lot. Wednesday night section is called Newton's method, and it's a calculator. Can I get a callus on the end of my finger kind of homework assignment. We're gonna use our calculator a lot, and by a lot I mean a lot. Hope if you have solar power, it would work great in here with me right now. So that's it for tonight. We'll do this again on Wednesday and then spring break's next week. No one's changing spring break. So spring break is still next week. So I'm probably going to do some.
Not next week. It's next to next week.
Oh, it's not next week. It's the week after next week, Rag?
It's after Easter.
Oh,
Like it
that's
starts
right.
with Easter.
You guys have the spring break that's not the same as the high school spring break. You're correct. So we have 2 weeks, and then you guys have spring break. That is 100% correct. Thank you. Nobody knows, including the people at Cal State, nobody knows why they don't match. We had a whole big rigmarole.
Even we did not match with BC. BC has different spring break.
Yeah, it doesn't match anybody's, right? I don't know why. It doesn't. So the unions got involved. It's going to match next year, so it'll be back. So we'll be back here. I mean, I'll still be here, but you'll still be there because where else are we allowed to be? By the way, just so you know where we're going with this, and I'm not trying to be a fatalist or pessimistic. My daughter lives in Virginia. I've told you that before. Her governor today decided June 10th is now the first day they can actually leave their houses. It's the first day any business can open. He's moved it all the way to June 10th. I don't know They don't have a lot of cases in Virginia. I don't know what his motivation for that is. I'm not saying we're going to do the same thing in California. I'm just saying that they're now all the way till June 10th. They're not, nobody can go to work. Nobody can do anything in Virginia until June 10th. So who knows? Who knows where this is going to go? So that's it for this evening. If anybody has any real serious questions, you can send them to me on Remind, and then I can try to see if I can get you some helpful hints back to you. It won't be instantaneous. Don't worry about that. All right. So I'm going to push the into meeting button down here. Just so you realize this, you guys can do this too. I mean, Zoom is free. I should have bought Zoom. It's gone up 5 times. It's 5 times more on the stock market today than it was when this whole pandemic started. But I didn't know what Zoom was. So if you want to work on your homework with other people in class, there's nothing to keep you from hosting a Zoom meeting yourself. It's free. It requires no work on your part. So thank you guys for being here tonight. Everybody have a great day. And what's left? All right, no worries. I mean, hey, I'd rather be doing this than what I was doing before, which was being bored. So this is a lot more fun for me, to be honest.
Beats the hell out of trying to learn it online too.
Oh, well, I hope, Adam, I hope it helps. I mean, I really do. I don't love what's happening here. This is not my idea of fun to try to teach this way. And I'll tell you guys this, not that you care at all. It is way more work for me to do this than it is for me to teach you guys in the classroom. I mean, I and my wife are putting in probably double the time it takes us normally to teach things to try to help our students learn this way. This is not efficient. But hey, it's what we're here for. It's what we get done. And so it'll be great. We're going to make it work. So I will see you guys on Wednesday night, same time. I'll send you another link on Remind for the next meeting, and then send you a little remind beforehand to make sure everybody remembers. And then I'll see you on Wednesday. All right, guys. Have a great night. See you soon.
Wait, what did I miss at the end because my internet crashed?
Oh, I was just telling everybody we're going to meet again on Wednesday. That's pretty much it.
Okay, because my internet is crashing really bad right now. It's starting to fail.
You didn't miss anything other than the example that's on the whiteboard right now, and I'll put that back up in case you didn't get a screenshot of that. And then I'll put that back up right now.
Thank you, Kevin. You have a good evening.
You too, guys.
Thank you.
So, I have a suggestion to you, Kevin. Can you make a personal ID so we don't have to log in a different ID?
Yeah, I could do that, Rag, but the problem is I have 4 classes I'm now doing on Zoom, and it's easier for me just to send you guys the links. I understand it's a little more work for you, but otherwise I have to open 4 Zoom accounts to have 4 different IDs so I can do 4.
No, it's not necessary. You can use only one for 4 different classes. It's not necessary.
Well, I'm going to just keep doing it like this.
Yeah, sure.
And so this is just the easiest thing for me. All right.
I think so.
All right. So there you go, Samantha. That's the last thing we did. And then we will see everybody on Wednesday night. All right. So everybody.
All right.
All right, guys. Bye-bye.
Bye. Thank you.
You're welcome, guys.